Hello. Today I will be talking about SAFKASI or SAFKASI, which is a security-based system, and it's a new and improved security-based stacking inspection system based on the Java programming language. It's a very interesting research paper. It's 28 pages long, and it was pretty relevant in terms of like language security, and that's why I am doing a critique on it today. So first things first, let's do a little introduction and let's talk about the research paper itself. So basically, this critique on the topic of language-based security is done on a research paper that's titled SAFKASI, a security mechanism for language-based system. And it was published to the ACM conference, so it's a pretty prestigious conference, by Dan S. Wallach from Rice University, Andrew W. Apel, and Edward W. Felton from Princeton University. So the authors want to tackle the issue of stack-based inspection security system in Java because they believe that while there is an inbuilt system, the system lacks the complete security to prevent dangerous calls, and this security-based system also interferes with processes that are very important to the functioning of the Java programming language, like tail recursion, and hence they're reducing the speed of the applications. So one of the biggest concerns was, and we'll talk about this later also, is the confused deputy problem. And that problem arises from unprivileged check methods that the JVM or the Java virtual machine decides to execute. We'll be covering all of this in a bit. So the authors basically in this paper, they're proposing a new system using stack-based inspection. But this stack-based inspection system is now based on one of the important fundamentals of programming languages and paradigms, a belief logic that is based out of a belief logic dubbed ABLP. And besides having the belief logic, it is also implemented using this security style for languages that's called security passing style that attacks those security concerns, or basically like solves those security concerns that arise from the logic system that this paper presents. So one of the good things about this paper is, we'll talk about the interpretation of the problem and how the solution is based on sound logical arguments and axioms, and it's really different for the time when it was implemented. There are some issues in implementation and runtime. It's not, no problem is completely always solved, but we'll also cover that in a bit. So let's talk about, the research paper in detail, or more about what we are planning to tackle. So there's 7 issues here that we're going to look in detail. Current issues with the current stack-based system in Java, the proposed solutions that the authors came up with, and why they thought that was a good solution. Then we talk about the logic part of the solution. Then we talk about the new semantics part of the solution. And then we go towards the optimizations part of the solution, because you're writing code, you're creating things, and can just lead to a lot of issues. The 6th topic that we are looking to target is basically the practical implementations of the solution, right? So how can you practically implement this? What issues did the authors come up with when they were implementing it, and stuff like that. And the 7th thing is runtime. How good did the system run? Any other issues? So this is like the slides for explaining the methods discussed in the research paper. And then obviously there's like, a summary of my own critique and my own opinion, and like the final conclusion. So moving on. Let's talk about, I assume, issues first. So the main thing to recognize here is that Java has a stack-based inspection system, right, that it implements for its own security. And some of the security implements a confused deputy problem. what a confused deputy problem means is that you're not sure where this method is running from in the chain of command, but like it's running from something that you think is authorized. So you're letting it run, but there's not 100% surety. And I don't have to explain this, but this seems like a huge security concern. So what happens is the specific issue that this paper tackles is the check privileges method. So check privileges method is a method that is run by the Java input output or IO library. And the idea of check privilege is that we, you know, ensure that no unprivileged methods are able to run in Java and mess up the system. And this is basically the root cause of problems because it is really easy to confuse the system. You can run an unprivileged Java method by passing that method into a standard Java IO library method. So if I have a standard IO method, you can pick any, and you run an unauthorized program, say find numbers or find rabbits, even though it's not authorized, and some other users running it, because it's passing another method, the stack-based inspection system believes that it's authorized and allows it to run. It's a huge vulnerability in the JVM ecosystem, and hence it's termed the confused deputy problem. Uh, Another issue is that even with this current stack-based inspection system, efficiency is very poor. If there's a program with a lot of recursion, that means, and this is going back into Java, in Java, everything is run on the idea of stack. So whenever you're running anything, it's added onto the stack that Java keeps. Now, what's happening is if there's a method that, uses recursion or follows a lot of things like that, you're going to continuously run into these issues because the depth is huge. And this stack-based efficiency method is very inefficient with it. It cannot run anything with lots of recursion. Tail recursion is hard to implement. And what that makes is it makes the application unportable. Making the application unportable is kind of a huge issue because that's the main point of making applications these days. And lastly, tail recursion is used to implement a lot of data structures, a lot of efficient algorithms. You really cannot use it with the current stack-based system. And that's the only language-based security system that Java is providing so far. So the authors looked at this issue and they came up with solutions. So there's 3 parts of their solution. First is coming up with a simple belief logic or programmatic logic that's not coded, but that's based on axioms and discrete mathematics. And this one's termed ABLP logic. We'll talk more about it in a bit. The second thing is new semantics for security passing style. So this essentially means that there are gonna have new logic, new theorems, new ideas, and new what do you call it? They have new structure. So new logic. And then the last part is static and dynamic optimization. So when you run ABLP logic, when you run new semantics, you end up with the issue of having overhead, but you want to make your application run in constant runtime. So you use static and dynamic optimizations. So first things first, what is ABLP logic? Right? First is the simple, so the first, and this is why I really like it, is 3 simple solutions. ABLP logic is number 1. This logic is based on program paradigm that was followed, that follows the logic from the 1980s that was of ABLP logic. And ABLP logic is very complicated and the research paper doesn't really get into it. However, there are 4 main areas in ABLP logic. There is one, the principal. The principal is the main driver method in this case, or the signer of the program. So every frame in the stack has a signer, and that's what the principal represents. Second is a target, and the target represents the resource that the program wants to protect. So it is something that Java attaches an access control to. Thirdly, statement. So statement, pretty simple, any command that the principal wants to do for the program or wants to run. And then this logic, so what happens is the fourth thing is a quotation, and the quotation is something that lets a principal decide on a logical action that another principal makes. So when you're making a security-based system, there are multiple principles. Quotation allows another principal to take, a logical decision like true or false, and whether they want to execute something that probably another principal that is maybe, a security vulnerability that is being recommended. So how this logic works is that it works in such a way that this statement is only trusted if there is trust in the principal. So that's how the logic is determined. So if the initial principal, the initial signer, does not have trust, then any frame that comes from that signer will automatically have a doubt labeled to it. Additionally, the principal cannot execute any statement that leads to a logical contradiction. So this Boolean logic that has been made, the principal is not allowed to execute a statement that results in a logical contradiction to this. So we're essentially not running anything. And what happens here is that based on this belief logic, the authors now do a mapping of this ABLP logic onto Java, specifically to handle, privilege calls and make a better stack inspection algorithm. So one of the things is, since, Java code is signed with a private key and then sent to the virtual machine, transitivity of logic is used to ensure that the signer's initial digital logic remains even if one of the frames of the stack are changed, because one method is being called by the other, and the logic works in such a way that the statement can only be trusted if the previous statement is trusted. And this is really good because this mapping allows us to, ensure that the Java bytecodes are not changed without the JVM, and that the JVM has to check the security of each stack. So this makes it more safer. Second thing is new semantics. So ABLP logic obviously brings up security vulnerabilities that needs two security passing style methods to check and ensure the security of the two subsystems that the ABLP logic generates. And this is what the new semantics do. So the idea is that there are two subsystems that need checking, and what the system does for that is they add implicit arguments to every procedure, hence removing the requirement to have a separate pushdown stack to check the security of the Java methods to ensure that no unauthorized program is getting called. Now, what happens is this security passing style, which does this checking with the pushdown stack, once written in that language, once it's written in SPS, you no longer need to explicitly call the functionality in JVM, making the JVM really lightweight and really portable. And this is because SVM parsing style occurs through the program, and only a few Java bytecodes are rewritten or added that the JVM needs to execute. And lastly, and I think this is very important, we don't need an extra stack to execute this, so it's strong. Okay, also, SPS ensures that the stack inspection modifications happen within Java language semantics only. So no logic from outside is used, or no incompatible logic is used, and security is applied within the JVM. So now, one of the examples is we run SPS on this function. This function has been taken from the research paper, and the idea is that it checks the previous owner, right? From the pushdown stack, it checks the previous owner. It makes sure there's no security vulnerabilities. Only then does it execute the two separate methods. And then finally, when it's running the check privilege method, now it's not checking the privilege method from the outside and making sure that it's true. It's checking the function that's been called inside the check privilege method. That really, ensures that higher security is there. Next, optimizations. So the optimization in this program is better than, what I think the Sun and Netscape implementations are, and there's also benchmarks for that, because in the Sun and Netscape implementations of Java, security is not bounded by size. In this case, security context is bounded by size. So there's two types of optimizations they do. They have static optimizations and dynamic optimizations. Static optimizations are substitutions based on ADLP axioms that allow for computations of functions inside the outer function initially, solving a problem. And basically, it's already running this. Second thing is, since you're calling one function inside the other function and it's used often, this substitution that we're making based on ABLP logic helps us save a lot of overhead in the future. Coming to dynamic optimizations, we're basically allowing lazy compute of values in the table for security context. So basically, till the time we are not running in the security context, the program does not compute anything at all and computes it later. So running into practical implementations, that was an issue, right? Open world problems have less information available that we can infer from. And optimization is hard in that, right? It's hard to make legal optimizations in it. Closed world problems on the ones that we're dealing with do not have those issues, so that's an issue. Secondly, performance is worse compared to an implementation of a closed world, as more factors and features must be taken into account. And open world implementations of new data coming in constantly. No data is being pre-processed and pre-compiled, which is one of the things that they assume, like REST APIs consume data at runtime, but this assumes that all the code is already checked before, so that's a big issue. So in terms of runtime, this is empty, but the idea of runtime was that there was a constant runtime of under 50 milliseconds for the check privilege implementation for a stack depth of over 18. However, the way practical implementation was done per method, the overhead became way more costlier. So in terms of summary, 3 big problems exist in the current stack. No real security, no ability to perform tail recursion or recursion checks at all, and not portable. The authors came up with a solution that was based on ABLP, new semantics, and optimizations. ABLP had 4 components, and they all are in conjunction with each other. Security passing style takes the problems of ABLP security vulnerabilities and solves those without an extra pushdown stack, and near constant runtime is achieved through static and dynamic optimizations, and there's a practical runtime for the stack depth. So critique. So one of the issues was, the good things about this article was the organization made it really easy to understand how and why a new system is needed and how Java 2.0 is really bad. Problem and issue that come up with one of the problems like ABLP, problems of ABLP get solved by SPF, SPF problems get solved by optimization, and it's a really good way of convincing the audience that this is what they should adopt. Every description of every method is done using formal logic and proofs using induction, so it's really hard to question, how valid it is. And through the description of formal logic and mathematics, the issues of security that the current system has is solved, and an example of unauthorized check method is used. Finally, 3-step solution brings out problems that the second solution tackles, and second solution brings out problems that the third solution tackles, and etc., etc. Critique 2. So this is the second part. I think one of the weaknesses of the article was its relevance. Article cites Java solutions that date back to Java version 2.0. We're now in Java 15.0. And your solutions from Sun and Netscape. Oracle runs Java now. Issues with prototype. Their prototype did not work well. They had assumption like closed set problems. SPS semantics could not be implemented in theory because you needed like extra stacks, extra semantics. It became a chicken and egg problem. You needed to add dummy overhead layer to solve that, more overhead, and it's not production ready. It doesn't take into account open world problems. It doesn't take into account like that we're using APIs and applets now. Security context info manipulation is not handled. So basically, if you can make sure that the initial method is just set to true, you can keep fooling the system. And there were no established benchmarks to check the system against. So that was an issue. In conclusion, issue of stack-based security parsing is a key issue that must be solved to hamper the entry of malicious code being run from unauthorized users. Research paper is important as it's a step towards tackling the problem. Theory is based on really good sound logic, although practical implementation might take some time as a lot of assumptions are made. Overall, the solution mentioned to the problem of security stack parsing is a good one, but issues like bootstrapping, use of reflection API, that's an unauthorized Java API, and they're not really checked, and it's not designed for open world issues, so that needs to be done. I think future work in this area should be, on implementing this production-wise for Java stack, for other languages in the open world system, and for big data issues as you're using terabytes of data now. And if the system can't go through that, it's not that useful. Yeah, and that's it. That's a presentation. I hope you all really liked it. Thank you so much.